We've discussed Retrieval-Augmented Generation, or RAG, in case number TCM 093001, but we didn't dig into its foundational architecture. Today, we look at the 2020 paper that introduced RAG and shifted how we think about LLMs.
Right. We know RAG helps LLMs stay factual, but what specific problem was this paper trying to solve with its architecture back when LLMs were still relatively new?
The core issue was that large pre-trained language models were shown to store factual knowledge in their parameters, but accessing and manipulating that knowledge precisely was still a challenge.
So models had facts, but couldn't always spit them out correctly or on demand, like knowing the capital of France, but struggling to give you the capital of Burkina Faso?
Exactly. The paper states, however, their ability to access and precisely manipulate knowledge is still limited. This led to performance issues on knowledge-intensive tasks.
That makes sense. If the knowledge is implicitly encoded in billions of weights, it's not easily retrievable or verifiable like looking something up in a database.
And critically, it meant these models couldn't tell you where they got their facts from. The paper noted, providing provenance for their decisions and updating their world knowledge remain open research problems.
That's the hallucination problem, or the knowledge cutoff problem, right? The model can't update its internal facts easily, and you can't trust its sources.
Precisely. The paper proposes a solution: pre-trained models with a differentiable access mechanism to explicit non-parametric memory can overcome this issue. Think of it as giving the LLM a searchable brain implant. Now, this is an analogy. Unlike a real brain implant, it's not physically part of the LLM's neural network, but a separate database it queries. The searchable part is exact. The implant part is a metaphor for a tightly integrated, learned access mechanism.
A brain implant that's separate from its main brain, but it can access it instantly and learn how to use it better over time? That sounds powerful.
That's exactly what they defined as Retrieval-Augmented Generation, RAG, models which combine pre-trained parametric and non-parametric memory for language generation.
So parametric memory is the LLM's weights, and non-parametric memory is this external explicit knowledge base. Combining them is the core idea.
And importantly, they aimed for a general-purpose fine-tuning recipe. Not just a hack for one task, but a broad architectural approach to improve LLMs across many knowledge-intensive applications.
A foundational method then, not a niche solution. That makes sense for a paper introducing a whole new paradigm.
This paper set the stage. Now let's get a clearer picture of what Retrieval-Augmented Generation actually means in practice and how these two memory types work together.
Let's break down the intuition of how this parametric and non-parametric memory combination actually plays out.
This blog post gives a really clear, concise definition. Retrieval-Augmented Generation, or RAG, is an architecture where a system retrieves external context and provides it to a model before generation.
That's a good starting point, but it's more sophisticated than a simple Google search. Google returns a list of links, and you have to click through and read. RAG's retriever directly provides content fragments, and the model is trained to integrate them directly into its output, without human intervention. The quick search part is similar. The direct integration and learning part is where it differs significantly.
That's a good analogy, but let's refine it. Imagine a chef who needs to make a new dish. They can use their existing knowledge, which is their parametric memory.
And the external context would be a cookbook they can open up and read, or a recipe from another chef. That's the non-parametric memory.
This chef analogy works well for understanding the separation of knowledge sources. The chef's inherent cooking skill and learned recipes are like the LLM's parametric memory. The cookbook is the non-parametric memory. Where it breaks is that the LLM isn't reading in a human sense, it's processing vector representations and incorporating them based on learned patterns, and it's optimizing this entire process through feedback. Exactly. The post clarifies the goal, to make outputs more accurate, current, and grounded in source material than the model could produce from weights alone.
So the cookbook provides the specific, verifiable details the chef's internal knowledge might lack or be out of date on.
The analogy holds for pitfalls too. If retrieval fails, the model may not have the information needed to answer. If the chef picks up the wrong cookbook or can't find the page, the dish will suffer.
And if the cookbook is great, but the chef still messes up the cooking part, the generation, that's a separate failure point.
The article warns, if generation fails, the model may ignore, misread, or overstate the retrieved context. Just providing context isn't enough. The model has to use it correctly.
It has to integrate it intelligently, not just paste it in. It's a two-stage process, and both parts need to work well.
This leads to the crucial point. RAG quality depends on both retrieval and generation. It's not just about having a great LLM or a great search engine, it's how they dance together.
That's a very apt way to think about RAG's combined strengths. It captures the two-stage nature of retrieval and generation working together. The main difference, of course, is that the research assistant has consciousness and understanding, while RAG is a sophisticated statistical model that learns to mimic this behavior.
This concept of external memory isn't new. Databases have been around forever. But the innovation here is making that retrieval differentiable and end-to-end trainable with the generator.
So it's not just a hard-coded lookup. The system learns what to retrieve and how to use it through training. That makes it much more powerful.
Right. Differentiable means that during training, we can calculate how much each part, the retriever and the generator, contributed to the final desired output. This feedback allows us to update both the retriever's ability to find relevant information and the generator's ability to use it simultaneously using gradient descent. This is unlike traditional search engines where you train the search and the summarizer separately and then just glue them together. Now that we have the intuition, let's go back to the original paper and see the specific components and mechanisms Lewis et al. Proposed to achieve this differentiable retrieval and generation.
Time to look under the hood. How did they actually build this system to combine an LLM with external knowledge?
The paper specifies the core components. For the parametric memory, they used a pre-trained seek-to-seek model. This means a transformer-based model, capable of both encoding input and decoding output sequences.
So a standard transformer encoder-decoder architecture, something like T5 or BART, which we've explored before, that handles the actual language generation.
And how does the generator use the retrieved passages? In the original RAG paper, these passages were typically concatenated with the input query and fed into the seek-to-seek model, usually through its encoder. The model then learns to attend to and integrate this retrieved context while generating its response, making decisions about what information to prioritize.
For the non-parametric memory, they explain it's a dense vector index of Wikipedia. Imagine Wikipedia articles broken into small chunks and each chunk converted into a vector embedding.
That's a good way to visualize it. The numerical fingerprint, or vector embedding, is key for finding similar sections. The library part is a metaphor for the vast collection of knowledge. It's not organized by physical location, but by semantic similarity in a high-dimensional space, allowing for efficient conceptual lookup.
To search this library, they used a pre-trained neural retriever. This retriever takes the input query, converts it into an embedding, and then finds the most similar vector embeddings in the Wikipedia index.
Yes, the librarian analogy is useful for understanding its role in finding relevant information. Where it differs is that this librarian doesn't understand in a human sense, but rather identifies patterns of similarity between your query's embedding and the document embeddings, learning to do this effectively through training based on the downstream task.
Exactly. The key here is neural. It's not keyword search. It's a learned system that understands semantic similarity. The retriever takes your input query, encodes it into a vector using an embedding model, and then compares this query vector to the pre-computed vectors of all the Wikipedia passages, typically using a similarity measure like dot product. It then selects the top n most similar passages. This process of encoding and comparing is what allows it to find passages conceptually related even if they don't share exact words.
That's crucial. Semantic search means it can answer questions like, what's the best way to make a cake, even if the document says baking a dessert. It understands the intent.
The paper explored two main ways to integrate the retrieved documents with the generator. They state, we compare two RAG formulations.
Different strategies for how the retrieved context influences the generation?
That's an interesting design choice.
The first formulation, one which conditions on the same retrieved passages across the whole generated sequence. The retriever runs once, finds a few passages, and those fixed passages guide the entire output.
So, the chef gets a recipe card and refers to that single card for every step of the dish. It's consistent, but might miss new information if the dish is complex.
The second, more dynamic formulation, the other can use different passages per token. This means the retriever can pull new, relevant information for each word or phrase it generates.
That's much more adaptive. The chef can look up a new technique for the frosting, then a different one for the cake layers as they go. It sounds more powerful, but also more complex.
The concept of a dense vector index and neural retrievers is foundational. It's built on embedding models and similarity search, ideas that are widespread in modern AI systems.
So the ability to turn text into these meaningful numerical representations, embeddings, is fundamental to how RAG works, enabling both the retriever and the generator to operate effectively and learn from each other.
These components form the basis of the RAG architecture. But even the most powerful tools have their limits. Let's discuss some of the inherent challenges.
Good point. It's important to understand where RAG might still fall short, even with its clever design.
While RAG is incredibly powerful, it's crucial to acknowledge its limitations. One key aspect is its dependency on the quality, comprehensiveness, and recency of the external knowledge base. If your dense vector index is incomplete, outdated, or contains biases or errors, the RAG model can still hallucinate or provide incorrect information, not from its own parametric memory, but due to flaws in the retrieved context. This is what we call retrieval-based hallucination.
So RAG doesn't fix hallucinations entirely, it just shifts the source of potential errors from the LLM's internal memory to the quality of the data it retrieves. And if the retrieval is good, but the LLM still misunderstands it?
Exactly. Even with perfect retrieval, the generator itself can still fail. As the article warns, if generation fails, the model may ignore, misread, or overstate the retrieved context. This highlights the ongoing challenge of ensuring the LLM intelligently processes and integrates the information it's given, rather than just copying or misinterpreting it.
So the searchable brain implant is only as good as the knowledge it holds, and the chef still needs to be skilled enough to use the recipe properly. It's a system, and every link in the chain matters.
Precisely. And training RAG systems effectively requires careful consideration of both the retriever and generator components, as well as the alignment between the external knowledge base and the specific tasks you're trying to solve. It's not a magic bullet, but a powerful architectural pattern with its own set of challenges to manage.
So, understanding these failure modes is crucial for anyone building or deploying RAG systems to ensure they're robust and reliable.
Indeed. This brings us to the end of our deep dive into the foundational RAG architecture. We've seen how it addresses key LLM limitations, the intuition behind its dual memory system, its specific components, and its inherent limitations.
A comprehensive look at how RAG evolved to become a cornerstone of modern LLM applications, and a reminder that even powerful systems have their caveats.